The actual chemistry of electroplating isn't incredibly complicated. In fact, it works as a result of fairly basic chemical processes. Elements such as chromium are pure chemical structures. All chemical matter in the universe is made up of elements or combinations of them. Each element consists of only one kind of atom. Atoms are the building blocks of the universe, so let's start with them. Every atom consists of a dense nucleus containing two types of particles, positively charged protons and neutrally charged neutrons. Orbiting in a cloud around the nucleus are negatively charged electrons, bound to the nucleus by electromagnetic force. Multiple atoms stuck together are called molecules. Each element is classified by atomic number, the total number of protons in the atom's nucleus. In their purest forms, the number of electrons and protons in an element are equal. The element helium, for example, has 2 electrons and 2 protons, so its atomic number is 2. The element with 3 of each is lithium, the element with 4 of each is beryllium, and so on. This is chromium over here, with 24 each of protons and electrons, living in the transition metals section of the periodic table of elements with all its family and friends. But atoms can lose, gain, or swap electrons, and that's when things get really interesting. An ion is an atom or molecule that's gained or lost one or more electrons, resulting in a substance that is positively or negatively charged, depending on whether protons or electrons outnumber each other. Given that an electron is something like 1/1,000,000th of a centimeter across, it may not seem like a big deal to lose or gain one, but ions often have very different properties than their parent atoms did. Some elements are very strict about how many electrons they're willing to give up or adopt. Calcium, for example, is like an overprotective mother. It's only willing to part with 2 electrons, and that's it. Chromium is a little more easygoing than calcium. It's okay with losing 2, 3, 4, or even 6 electrons. For platers, the important chromium ions are those that have lost 3 or 6. They're called trivalent and hexavalent chromium, respectively. Keep in mind that it's all still chromium. Losing electrons doesn't mean chrome loses its identity. It's just in a different chemical state and capable of behaving differently than other ions of itself would. So how do you make a chrome plating bath? Basically, you need to dissolve chromium in water. Unfortunately, pure chromium is a metal and doesn't dissolve easily. However, certain chromium ions are very happy to bond with ions from other elements to form compounds, typically oxides or salts, and these dissolve in water just fine. Hexavalent chromium ions, those are the ones that have lost 6 electrons, can bond with oxygen ions to form chromium trioxide. It's sort of a dark reddish-orange solid that can be ground up into flakes for easy dissolving. When you pour chromium trioxide into water and stir it up, the result is chromic acid. That's not the only ingredient in a plating bath, but it is the most important one. A word of caution here. Certain compounds, including chromium trioxide, generate a lot of heat when added to water. You should always wear safety equipment and exercise caution when mixing a plating bath. We may be lightening things up here just for fun, but safety is something you always want to take seriously. So we've poured our chromium trioxide into the water and stirred it up to make chromic acid. But on its own, that's not enough to be a plating bath. Another key ingredient is the catalyst. In chemistry, a catalyst is something that triggers or speeds up a chemical reaction, but isn't consumed or changed in the process. You never have to add more catalyst, but in many cases, including chrome plating, the reaction won't happen at all unless a catalyst is there to give it a push. So let's talk about the 3 most popular types of plating baths according to the catalysts each use. The conventional single catalyst plating bath dates back to the 1920s, and it's still the most widely used today. It's very affordable and doesn't require a lot of maintenance or attention. This bath uses an ion of the element sulfur as a catalyst, in the form of sulfuric acid. To make this bath, add chromium trioxide flakes to water until the chromic acid concentration is about 33 ounces per gallon. Next, pour in sulfuric acid until the chromic acid to sulfate ratio is about 100:1. So if you had the target 33 ounces per gallon of chromic acid in your bath, you'd want 33/100ths of an ounce of sulfate per gallon. That's about 2 teaspoons per gallon. Whenever you're mixing acid and water, pour the acid into the water, not the other way around. Never pour water into acid, unless you want the mixture to fizz up and potentially melt your face off. The conventional single catalyst bath is nice because it doesn't attack metals like steel and aluminum, which means you don't have to mask areas of your part that you don't want damaged. Just shield them so they don't electrically communicate with the anodes, and that way they won't get plated. The single catalyst bath isn't perfect, though. Its biggest problem is efficiency, so parts take longer to plate, and the chrome it plates tends to be less corrosion resistant than plating done in other baths. This kind of bath produces a coating with few micro cracks, which can be good depending on the application of the plated part is meant for, but the cracks it does produce are also longer and deeper than is usually desirable. Finally, single catalyst baths are very sensitive to power changes. Even a small fluctuation in power can result in dull, soft, or peeled chrome. Despite these issues, though, the conventional single catalyst bath remains very popular, and it's a common sight at most plating shops. The fluoride mixed catalyst bath offers some improvements over the conventional single catalyst bath, but also has some unique disadvantages. It's basically a conventional single catalyst bath with another catalyst, in the form of fluoride ions. Less sulfuric acid is used in this mixture since the presence of fluoride balances it out, but once again the amount of all ingredients can vary somewhat as long as the ratios between them remain constant. The fluoride mixed catalyst bath is much more efficient than the single catalyst method, so parts are plated faster and the process consumes less power. The deposited chrome tends to be more corrosion resistant thanks to the more favorable micro cracks, with a nice network of thin, shallow ones. The fluoride bath is also less sensitive to power fluctuations. It costs a little more than a conventional bath, but it's still not very expensive since all the chemicals involved are pretty common. The real disadvantage of a fluoride mixed catalyst bath is that it chemically attacks unprotected areas of the workpiece or rack, causing bad etching and potentially damaging the part so badly that it's ruined. That means very aggressive masking is necessary to protect every unplated area of the part. In fact, sometimes the fluoride bath can even etch the areas being plated. So long as great care is taken in masking parts, the fluoride mixed catalyst's benefits are significant, but platers do need to be aware of the disadvantages. The final bath we'll discuss in detail here is called the high-speed, non-etch proprietary bath. This mouthful offers all the advantages of a fluoride bath, but doesn't attack exposed metals submerged in the fluid. The supplier is keeping the ingredients that allow for this a secret. Chrome deposited by this bath shows excellent hardness and the most favorable micro-crack structure of all the baths we've discussed. It's also extremely efficient, plating even faster than the fluoride bath. Drawbacks? Well, because the supplier is being so mysterious about the ingredients, only they can sell it, which makes it by far the most expensive bath to maintain. It also requires a little more attention and maintenance than the other baths. You may need to add additional chemicals now and then to keep it working efficiently. Hard chrome plating is an electrochemical process, meaning that electricity is going to get involved sooner or later. The chemistry part is what makes the chrome bath capable of plating. The electricity part allows that action to take place. In some ways, electricity works very much like plumbing. There are also significant differences, of course, but the image of a plumbing system can be useful to visualize the process. For our purposes right now, we need to know only two key electrical terms: amperage and voltage. Returning to the plumbing analogy, amperage, usually shortened to amps and also referred to as current, is the amount of electricity flowing through a conductor. So it's the equivalent of the amount of water in a pipe, even to the point of being able to move more current through a thicker conductor, just as you can move more water through a wider pipe. Voltage is electrical pressure. Essentially, it's how hard the amps are being pushed through their conductor. If you imagine a high-pressure fire hose versus a common garden hose, you can visualize the difference. By varying amps and volts, you create situations with high or low pressure and current, and the optimal balance allows us to plate hard chrome. In order for deposition of chrome to take place, the part, called the cathode, must be connected to the negative terminal of a direct current power supply, and lead alloy anodes must be connected to the positive terminal, Then the current flow can pass through the bath. You'll note we said direct current. That's a problem, because most traditional power isn't direct current. It's alternating current. Alternating current, or AC, is the kind that most power companies make and most consumers use. It's easier to generate, easier to store, and easier to transmit over long distances. AC gets its name because the current flow cycles, or alternates, between positive and negative voltage polarity, like the waves in an oscilloscope. It starts at 0, climbs up to positive, then goes down, passing 0 and into negative, then back up. Each time it does this is a cycle. In the U.S., this cycle happens 60 times a second and is measured with a unit called hertz. The plating shop gets AC power from the power company just like everyone else, but we need direct current, or DC, and DC doesn't work the same way at all. Direct current is consistent. It doesn't alternate polarity. It's both positive and negative all the time. The most common producer of DC power is a battery. Both car batteries and the ones you'd use in a flashlight produce direct current. The key to getting a plating system to work is converting standard AC into DC. We accomplish this with a device called a rectifier. A rectifier's thyristor acts as a one-way valve, essentially only allowing current to pass in one direction or polarity. The trick is that a rectifier doesn't produce a perfectly straight, constant voltage like true direct current. It produces a slightly wobbly line, one that goes up and down in voltage just a little bit. This is called ripple. With a good enough rectifier, these ripples are usually small enough that they won't mess up the plating process. Successful chrome plating is all about power, and plating shops have a wide selection of choices when it comes to what power supplies they want to use. We're not going to go over them in agonizing detail here, since the important ones are discussed at length in the handbook. However, we will do a quick review. The power supplies in most common use today are variable power stats and silicon-controlled rectifiers, or SCRs. They're good workhorses, allowing for some level of manual control over current output, and each has specific advantages and disadvantages that you can read about in the handbook. Switch mode units are the newest technology on the block. The positive to negative ripple in a switch mode unit's rectified DC current is usually less than 1%, which makes it especially good for hard chrome plating, a process that's very sensitive to current fluctuations. These units are programmable and so small and light that they can often be mounted on a wall near the bath. There are a lot of factors that come into play when you're choosing the appropriate power supply for a plating shop. Cost is obviously important, but you should also consider the amount of power needed. Large parts, and tanks with many parts being plated at once, call for higher levels of current than smaller operations. Generally, the more surface area you're trying to plate at one time, the more power you'll need. Placement is also important. If the power supply is not going to be near the tanks, it may be necessary to include some remote control and monitoring equipment, and to invest in better connections between the supply and the tanks to minimize current loss along the way. Finally, you've got to think about ripple. Some electroplating and electrostripping operations are very tolerant of ripple, but hard chrome is not. Any significant variance in the current can have severe impact on the adhesion of the chrome and even the properties of the chrome that does get deposited on the part. The decision requires careful consideration not only of the shop's current needs, but possible future needs as well. Rectification of AC power to DC isn't 100% efficient. Some of the energy is lost as heat. Delicate power supplies are sensitive to heat, so it needs to be removed or it'll cause inefficiency and damage. Air cooling is the easiest way to do it. Room temperature air is blown across the power supply and scoots heat out the other end. You can use this air to warm the shop if it's cold outside, or just vent it away. The problem with air cooling is that it's not super efficient at moving heat, and even the best systems use loud fans that can get annoying. Water-cooled supplies work by passing water over the hot parts and then either cooling the water in a radiator or by exchanging the hot water with cold, cooling the hot stuff with a chiller or cooling tower and then swapping back. Water is a much better conductor of heat than air is, and any kind of water cooling will almost certainly be quieter. Water cooling systems are expensive, though, and leaks can pose a serious problem. Water and electricity don't mix. Chrome electroplating is low voltage but high current, and it takes a lot of infrastructure, called busing, to move all those amps from the power supply to the plating tank. This section is about how the power gets from the supply to the bath where the chrome plating actually happens. The first step is to get the power from the rectifier to the tank bus, which actually holds the parts that go into the plating bath. The low voltage of hard chrome plating is a bit of a disadvantage, since so many amps moving through a bus with so little pressure means that some current will be lost along the way. Copper cables or bars are used for rectifier busing, and the general rule is that the diameter of the copper should be 1 square inch for each 1,000 amps carried. In shops where the rectifier is more than 20 feet from the plating tank, you need even thicker copper, but since copper is expensive, shops try to calculate exactly what they'll need. The rectifier busing doesn't connect directly to the racks of parts that go into the plating bath. It connects to the tank busing, which in turn connects to the racks containing the parts and anodes for the bath. There are two main types of tank busing configurations, 3-bar and 2-bar. There's a difference between rectifier busing and tank busing. The former transmits power from the rectifier to the tank. The latter transmits power into the bath and the part to be plated. The 3-bus bar design uses 3 bars in parallel. Stick anodes are attached to the outer bars, which carry the positive current. Anodes tend to be left in the tank all the time. The center bar supports the parts to be plated, and it carries a negative charge. In a 2-bus bar design, a negative bus bar runs along one side of the tank, and a positive runs along the other. Specialized racks containing both the part to be plated and the anode are placed at intervals between them. A benefit of a 2-bus bar design is that you can plate more parts in the tank simultaneously than you can with a 3-bar design. A plating shop has a lot of equipment needs, ranging from the very mundane to the very complex. The chemical and electrical requirements of such a shop also feed into what equipment is most necessary. A hard chrome plating bath requires a specialized tank, and usually some support tanks for related activities. The tank is a very major consideration. Chromic acid is serious stuff, and keeping a tank of it heated and ready for plating requires careful planning by qualified engineers and tank designers. There are huge environmental and safety issues associated with tank leaks, not to mention the personal hazards of working around such toxic and corrosive chemicals. Cleaning prior to plating is more critical than almost any other step in the plating process. The part to be plated must be cleaned very thoroughly to remove any grease, dirt, dust, or foreign material, which can interfere with plating efficiency and introduce contaminants to the bath. Not only is chromic acid corrosive and highly toxic, but the mist that rises off the bath is too. As such, chrome plating tanks have to be sturdy because of the acid and because they usually support a lot of heavy equipment. Bus bars, lead anodes, heaters, and so forth. Plating tanks themselves are made out of high-strength steel, lined with a heavy industrial composite polymer to protect their insides from the acid. The lining is designed to resist the acid, but it still needs to be replaced every 4 to 7 years. In addition to the tank itself, a hood and exhaust system is needed to keep the toxic fumes from the acid under control. A leak from a chrome plating tank would be catastrophic to the environment. Because of this, tanks should have 3 layers of protection against leaks or failures. The first 2 are the lining and the steel tank itself. On their own, though, both could eventually fail. The third barrier is a containment pit situated below the tank. This should be made of steel-reinforced concrete covered in a chemical-resistant coating. The pit must be large enough and durable enough to hold the entire contents of the tank until it can be pumped out. The containment pit is the last line of defense separating unbelievably toxic chromic acid and the groundwater beneath the building. Tank designers cannot take these safety precautions too seriously, and we'll discuss them in more detail in the Health and Environment section. Along with the main chrome plating tanks, a shop usually has some other baths to support its operations. You can learn more about these in the handbook, but briefly, common support tanks include an alkaline electrostrip tank, which is kind of like the plating tank's evil twin. Its job is to strip off deposited chrome. There are also etching and cleaning tanks that can be filled with a variety of solutions to clean recently plated parts. and rinse tanks, in which parts are rinsed with water to remove the last of the dangerous chrome solution. Cathodes and anodes are the key to the chrome plating process. Without them, the bath would just sit there and nothing would happen, because chrome plating is a process that depends on the flow of electricity through two submerged electrodes of opposite polarity. The cathode is the part to be plated. Cathodes have negative polarity, and the part is always connected to the negative pole of the power supply during plating. The item connected to the positive pole of the power supply is the anode, and it's a little more complex than the cathode. Anodes must be made of something that doesn't easily corrode, even if it sits in a bath of chromic acid all day. For hard chrome plating, lead is the material of choice for anodes. Usually it's mixed with a little antimony or tin, because pure lead is too soft to maintain its shape, but it holds up well in the acid environment. Unfortunately, anodes also need to be good conductors, and lead isn't really great at that. For this reason, some lead anodes have copper cores for improved conductivity. Anodes come in multiple shapes and sizes, which you can read about in detail in the handbook. Briefly, though, stick anodes are just lead cylinders hung off the racks into the bath. The drawback to stick anodes is that they're usually far away from the cathode, so more voltage is required to accomplish the same amount of plating than with conforming anodes. These are better than sticks. They're built to match the shape of the workpiece, surrounding it with anodic surface area equidistant from every part of the cathode. This leads to very uniform deposit thickness and requires less voltage. An exciting new anode technology is no-mask conforming anodes. These are normal conforming anodes encapsulated in plastic housings that act as masks for areas of the workpiece that aren't meant to be plated. This reduces or eliminates the need for masking. Along with the chemicals, the electricity, the busing, the anodes, and the cathodes, hard chrome plating baths need just a little more love to work. This love comes in the form of equipment that heats, cools, and stirs the bath. Hard chrome plating baths have to be heated, usually to around 135 degrees Fahrenheit, because the process works best at that temperature. Various types of tank heaters are used to keep the solution warm, and like everything else, they must be able to withstand the harsh conditions in the tanks while maintaining an even temperature. Ironically, chrome plating tanks also require cooling to maintain temperatures during lengthy plating cycles. The reason for this is that hard chrome plating is electrically inefficient. A huge amount of energy is lost as heat rather than being put to work plating the part, and the heat released into the tank warms up the bath. It's the cooler's job to undo that. Most cooling systems work by pumping cold water through tubes submerged in the tank. As usual, this system has to withstand the harsh conditions in the bath and should be inspected regularly for corrosion or damage. Finally, plating shops agitate their baths to keep the chromic acid moving throughout the plating process. Not only does agitation help even out the temperature, it can improve plating quality by dislodging hydrogen bubbles that tend to form around parts being plated.